So monohybrid crosses, and today is, like we said, 4/1/19. Mono means how many? One. So in a monohybrid cross, we're looking at one particular trait in the mating outcome for two individuals. So we're looking at one trait at a time. And what I've given you on the packet, this is just 6 of the traits from the beavers. I used to do this with your actual beaver babies, but it got way too complicated. So I just gave you some genotypes for some parents. This is a mother and a father. We've got their genotype and phenotype listed. And we're going to do some monohybrid crosses. So in a monohybrid cross, you might remember, this is the little box like this, and you put the letters on the top and you drag them down and you come up with some probabilities. Sound familiar? Okay. Now what I did on this worksheet is I gave you spaces for the gametes, and let's talk about those. So the first thing to consider, and we're gonna go ahead and just do big B for the mom, and big B, little b for the dad. I'm not even sure if that's one of the genotypes that's on that chart that I gave you, but that's what we're working with. So for, this is fur color, I believe, is the B's. Oh no, eye color. So for eye color, this is, here are a couple more vocabulary words we have to use. Both parents are heterozygous for eye color. What does hetero mean? It means different. So when I say what does homo mean and everybody goes, means same. If you are homosexual, you are attracted to people with the same plumbing you have. If you are heterosexual, you are attracted to people with different plumbing than you have. Same and different. So both of those are heterozygous individuals. If I said big B, I didn't mean to. I meant to make them both heterozygous. So both are heterozygous for eye color, 2 heterozygous parents. That's their genotype. Would these parents have the dominant phenotype or the recessive? They would have the dominant because they've got one dominant gene. And as long as you've got one dominant gene, it hides the recessive. So the effect of the recessive is hidden by the dominant gene. So here's the big question. When this female makes eggs, when her body manufactures eggs, what do those eggs contain? They only get half her genetic material. Well, there's a 50% chance her eggs are going to get the dominant allele. There's a 50% chance her eggs are going to get the recessive allele. What about the dad? 50% chance his sperm are going to get the dominant allele. 50% chance they're going to get the recessive allele. So there's a 50% chance of him passing on the dominant and 50% chance of him passing on the recessive. So the Punnett Square that I've given you, the way I've laid these out, there's actually a box to put in the gamete options, and we're going to typically put the mom's genetic contribution across the top and the dad's genetic contribution down the side. So for mom, she might pass on a big B, she might pass on a little b. For dad, he might pass on a big B, he might pass on a little b. Is this seeming familiar? Now, and you should remember this from middle school, you pull these down and you're just figuring out probabilities. So what we have are 4 boxes that represent the probabilities for genotypes for their offspring. Now, a couple of notes. When we're talking about a single trait, the dominant allele always gets listed first. When we're talking about multiple traits at once, some other stuff happens. But when we're talking about one trait, dominant allele always goes first in the genotype. Now, the thing that we're always interested in when we do this is the ratios of genotypes and phenotypes in the offspring. I know you can do a Punnett Square. I can train a chimp to do a Punnett Square. What I can't necessarily train a chimp to do is recognize the ratios that we're going to expect to see in the offspring. So the first one we do always is the genotype ratio, and I'm going to shrink my little gametes here. So there are 3 possible genotypes for these offspring. There's big B, there's big B, little b, and there's little b, little b. In other words, homozygous dominant, homozygous recessive, and what did I just write there? That was not what I meant to write. Heterozygous. Okay, so those are the three possible genotypes in their offspring. Now what we want to know is how many of each of these do we see? Well, how many, oh, and one other thing. When we're listing genotypes, we always list them in this order. Always, 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 always. It's really important that we do that because the ratios are standardized, and we typically, when we talk about them, when biologists talk about them, they'll just use the ratios, which means they assume everybody's putting them in the same order. So always put them in that order. Always list all three, even when all three don't exist. Okay? All right, so how many homozygous dominant do we have? 1. How many heterozygotes do we have among their offspring? Hold up fingers, don't yell it out. How many heterozygous? 2. 2. And how many homozygous recessives do we have? 1. So the ratio of offspring here for genotype is 1 to 2 to 1. And that's a really classic ratio that when we cross two heterozygous parents, the genotype ratio in their offspring is 1 to 2 to 1 always. Now, what about phenotypes? So this is brown eyes versus red eyes. So the phenotypes possible are brown eyes or red eyes. Well, how many brown-eyed offspring do I have here? So let's walk through these. Is this one brown-eyed or red-eyed? Brown. Are these two brown-eyed or red-eyed? Brown. So that's 3 brown eyes. Who's my only little red-eyed offspring? There's one in every family. We have 1 red-eyed offspring. So what we have is a 3 to 1 ratio of the dominant phenotype to the recessive. And we always put the dominant phenotype first because biologists will say, well, you know, we're seeing a 3 to 1 phenotype ratio. Parents must have been heterozygous. Okay. Now, a word about 3 to 1. And what percentage of the offspring would we expect to have brown eyes? Don't yell it out, jot it down. We would expect on average that 75% of the offspring of this pairing would have the dominant phenotype. About a quarter of their offspring would have the recessive phenotype. Does that mean if they have 4 babies, they will have 3 brown-eyed babies and 1 red-eyed baby? So let's do one for inheritance of biological sex. So we've got mama, who's biologically XX. We've got papa, who's biologically XY. What's every single one of her eggs going to contain from a sex chromosome perspective? X. She has nothing else to contribute. All her eggs are X. I was trying to do all my X's live in Texas, but it didn't really work out. What about his sperm? Half of his sperm will have X. Half of his sperm will have Y. Sex determination is entirely dependent on sperm. So when King Henry VIII was murdering his wives because they kept producing daughters, it was actually his fault. Oops. Just biological facts. So when we look at percentage inheritance for sex, what percentage of these offspring are female? What percentage of these offspring are male? 50-50. So let me ask you, who here has 1 sibling, exactly 1 sibling? Okay, so your sibling must be a boy, right? What about you? You have a girl sibling, right? What? Okay, wait a minute. You have siblings, right? How many of you total are there? 4. So it's 2 boys, 2 girls, right? What? Your parents are doing it wrong. Go home and tell them. You've got a bunch of siblings, right? Even numbers, boys and girls? Really? This is not possible because it clearly, we showed it with a Punnett Square, it has to be 50-50. So you have, there are 4 males and 1 female produced from the same 2, well, that's not possible. Well, you've got 3 sisters missing. You should go out and find them. I don't know where they are. Are there just 2 of you? There's more than 2 of you. So you've got at least 1 sister, and then 2 brothers, so it's 2 and 2? Okay, I don't know what's happening around here, but clearly, like I said, your parents have screwed something up terribly. There has been a dreadful mistake. Because the odds are 50-50, does that mean that if you have 2 offspring, one will be a boy and one will be a girl? No. The odds at conception every single time, rolling the dice, are roughly 50-50. Now, there are some other factors that play in, and we'll talk about, families that have six lovely little girls or, 8 boys in a row. By the time you get to offspring number 3, the odds are no longer 50-50 because of some chemistry changes in the mom's body, actually. So after you hit child number 3 of the same sex, it's like 57-43 that you'll continue to have that sex, and the odds go up and up. The odds of having an opposite sex decrease after that, and that's all due to mom's body chemistry. It's really weird stuff. So it's not necessarily, now if we talk about sample size, remember talking about sample size earlier? You have 2 kids, yeah, you can have 2 boys, you can have 2 girls, you can have 3 girls, you could have 6 girls, just ask my cousin Jimmy. If you had 100 kids, you would expect that you would start to approach a 50-50 ratio because your sample size would be large enough. Now, we figured out what that would take in the other class, and if we assume that a woman becomes pregnant for the first time at 15 and for the last time at 35, and that between pregnancy and then subsequent caring for the infant, she becomes pregnant every 2 years, that's 20 years, 10 pregnancies, so she'd have to have a litter of 10 every time. Probably not going to happen. But you would expect that you would start to approach that kind of ratio. Nobody should try to have 100 babies. It's a bad idea. If this couple of beavers have 20 offspring, we would expect that somewhere around 14, 15, 16 of them are probably brown-eyed. We would expect those ratios to start to do pretty well as the sample size gets bigger. Could they hit the odds specifically and have 4 babies, 3 brown-eyed and 1 red? Yeah, they could. But it could also, miss that. So what I'm going to have you do right now is complete 2 monohybrid Punnett squares on your own. The rest will be homework. Then we're going to talk about dihybrids. So most of you are already done with your 2. Let's talk about what happens when we breed a homozygous dominant and a homozygous recessive. All the siblings got the same genetic combination. What are the possible things that she can contribute to her eggs? Big B. What can he contribute to his sperm? It's pretty boring. Little b. You can actually do this, and a lot of people will do this in a single square. Some people go ahead and do this because it's confusing otherwise. But the point is, everybody's the same. So when we look at genotypes, we still write all 3, and it's 0 to 4 to 0. Because they all are heterozygotes. They're all heterozygous. 0 to 4 to 0. Now for phenotypes, and this is still, I did the brown eyes, red eyes. How many brown eyes do we have? 4. They all have brown eyes. How many red eyes? Zip. So it's still 4 to 0 dominant recessive. Now here's a question. So you get a whole litter. Let's say this is mice, and this is actually a trait in mice. We recently got mice at my house. Bo's Pet Shop in Columbiana breeds their own, and they have a tank of black mice and they have a tank of white mice, and they breed them there. Now, if you had a bunch of brown-eyed mice that had a brown-eyed father and a red-eyed mother. How could you prove that those babies, these babies right here, were harboring a recessive gene? What would happen if you bred any of those babies? If you bred those babies, about a quarter of their offspring would pop up with red eyes, which would be the proof that there was a recessive gene hiding in there. You couldn't see it in their parents, but you'd be able to see it in the next generation. And breeders will actually use techniques like that of breeding, breeding members of a particular generation to show that there's a recessive in there and to get an individual who has that recessive gene. Okay, questions, comments, concerns on monohybrids. Di means how many? 2. So monohybrid crosses were where we were crossing a single trait at a time. We're looking at one pair of parents and we're crossing one trait at a time, and we're looking at the ratios of genotype and phenotype present in their offspring. We're not done. Put it. Now I'm going to tell you this. There have been dihybrid squares on the air test every year. Monohybrid squares are a middle school standard. They don't assess those. That's too simple. There has been a dihybrid square every single year, including some with incomplete dominance. So we're going to do the hardest examples, but we're going to start off just getting your feet wet here. So just like with the monohybrid, the first thing we have to figure out is what's in the gametes. What's in the eggs, what's in the sperm. So let's take a mother who is heterozygous for 2 traits and a father who is also heterozygous for 2 traits. And we're going to do what's called a probability branching diagram. There's a better name for it. Ask your math teacher. I can never remember it. Every single time that this female produces eggs, there's a 50% chance that her eggs will get a big B and a 50% chance her eggs will get a little b. I'm going to shrink that a little bit. Now, of those big B eggs, there's a 50% chance that her big B egg will get a big N, and a 50% chance that her big B egg will get a lowercase n. And of her little b egg, there's a 50% chance it will get an uppercase N, and a 50% chance that it will get a lowercase n. All right, so there are 4 possible combinations for her eggs. Guess what we have for dad's sperm? Same thing. 50% chance they'll get a big B, 50% chance they'll get a little b, and of those, 50% chance that each big B, actually I should just take these and copy them and put tails on them. That would be easy. Well, okay. Let me shrink this. %50 chance that they'll get either of those. So there. There. Okay. So we've got the same possible combinations for dad's gametes. Now, to show those combinations on a dihybrid Punnett square, we have to use one of these bigger Punnett squares, and that's what you've got on the page. So we're going to do one sample together. That's this. We're going to put mom's combinations across the top. So she has big N, big B, big N, big B, little n. Little b, big N, little b, little n. This is where somebody usually says, well, wait, I thought the big letter had to go first. It does if we're talking about the 2 alleles for the same trait. Here we're talking about independently assorting these things. And I will say, all of this assumes that these traits aren't connected in some way, that they're being passed to the offspring independently. So dad's possibilities are the same: big B, big N, big B, little n, little b, big N, little b, little n. Now, to calculate the possible combinations for their offspring, we're going to do the same thing we've been doing, but we're going to reunite the alleles for each trait. So we've got big B, big B, big N, big N. Big B, big B, big N, little n. Big B, little b, big N, big N. Big B, little b, big N, little n. I feel like I'm in a Dr. Seuss book. Big B, big B, big N, little n. Big B, big B, little n, little n. Big B, little b, big N, whoops, little n. Big B, little n, little n. Big B, little b, big N, big N. Big B, little b, big N, little n. Little b, big N, big N. Little b, little, big N, little n. Good Lord, big, little. Big B, little b, big N, little n. Big B, little b, little n, little n, little n. Little b, big N, little n. Little b, little n, little n. Whew, that was exhausting. You might have guessed this. We have to do ratios. The key is that you should be able to look at a cross eventually and off the top of your head predict the percentage of the offspring that will have a particular combination. That's what they want you to be able to do. So, just like it was really important that we wrote those other ones in a particular order, we're going to start with three big B's. And the person who wrote this worksheet, that'd be me, didn't give you enough space for all the ratios you need. I apologize. I will fix it. So we've got big B, big B, big N, big N, big B, big B, big N, little n, big B, little n, little n. Then we have the big B, little b's. Big N, big N, big N, little n, little n, little n. Little b, little b, little b, little b, little b, little b. Big N, big N, big N, little n. Whew, little n, little n. Hoy. Circling these things is really important, marking them off somehow. I get all confused if I don't. And I know what should show up. All right, so how many homozygous dominant for both traits do I have? Well, I see this one. Any others? Nope. Homozygous dominant for eye color, heterozygous for ear color. I see 1, 2. Homozygous dominant and homozygous recessive, I see 1. Okay. Now, what about heterozygous for eye color, homozygous dominant for ear color? I see 1, 2. That should be it. What about homozygous for both traits? 1, 2, 3, 4. What about homozygous eye color, or heterozygous eye color, homozygous recessive for nose color? I see 1, 2. So we got 1 to 2 to 1 to 2 to 4 to 2. If you were a betting kind of person, what would you bet the ratio on those last three is going to be? Well, I bet you're right. Let's count. So homozygous recessive and homozygous dominant, I got 1. Homozygous with a heterozygous, I got 2. And I've got 1 little homozygous recessive for everything left. And that's hard to read. So what's the ratio? 1 to 2 to 1 to 2 to 4 to 2 to 1. I guess I got to move that over. To 2 to 1. Now, the easy thing is that there are only 4 possible combinations for phenotype. So you can have brown eyes, black nose. You can have brown eyes with a pink nose. You can have red eyes with a black nose, or red eyes with a pink nose. That's not so bad. How many of these individuals have brown eyes and a black nose? Well, let's go down and, okay, so these guys are dominant for both characteristics, right? That's 1, 2, 3. Oh, that one's recessive on the nose. Dominant for both. That's 5. Dominant for both. 5 plus 9. We're up to 9. Everybody else is recessive for something. What about brown eyes and a pink nose? Well, that'd be this one. And this one. Oh, these 2. So that's 3 of them. What about red eyes with a black nose? Who's that? Well, let's see. All our red eyes are down here. So these guys are red-eyed with a black nose. That's 3. And we've only got 1 individual that's recessive for both characteristics. So the ratio for phenotype, 9 to 3 to 3 to 1. And that's a classic when we mix 2 traits together and they're independently assorted. We get 9 to 3 to 3 to 1. Your homework. Finish all the monohybrid squares that are there. You should have 3 of them done. I think you've got 3 to do, or 2 to do. I forget how many. I want you to attempt 1 dihybrid on your own. When you come in tomorrow, we're going to work on dihybrids. We're going to ask some questions, and we're going to run through some scenarios. Okay?